In this section, we are going to talk about compound inequalities. Earlier in the chapter, we talked about inequalities that looked like this. Second, x is less than 2, or x is greater than or equal to 5. But compound inequalities will have more than one inequality symbol. That's why we call them compound. And they are broken up into two different categories: and compound inequalities and or compound inequalities. And is talking about what we call an inclusion or overlap. Or is talking about two separate sets of solutions. Okay, so if you look at this one on the left, the and statement, it says x is greater than 4 and x is less than 9. The way you see it written most of the time in textbooks is this right here. What this says is that x is greater than 4 and less than 9. Exactly what the statement above said. Another way to say it is that x is in between 4 and 9. If you look at the or, this says x is less than 4 or x is greater than 9. Those are no longer numbers in between 4 and 9, but going in opposite directions. If you look at the number line graphs, you can see that with the and compound inequality, the graph is in between those two values. And or, they are two separate. Here is one memory device that you can use to help and remember the difference between and or. And I call it an and sandwich, where the graph is sandwiched in between two values. I remember or by thinking opposite or outside, where the values are on opposite or outside of the two numbers. Solutions for and are found in both inequalities. That's what I was talking about with overlap. And with or, they're in either one. You won't find a value that's in both, that's less than -4 and also greater than 9. It's either or. So you can write both compound inequalities as two simple inequalities, but and most of the time, again, is written joined, where the smaller number is on the left, bigger number on the right, x in the middle. So it says which has more whole numbers, whole number solutions, the and or the or statement. The way I think about it is if you look at the number line graph for the or, those arrows could go on forever in the direction to the right and forever in the direction to the left. While the and only has a contained set distance. We call this a bounded graph. This is unbounded. It goes forever in both directions. So that would mean that or compound inequalities have more solutions. Number 2, it says list 3 whole number solutions to the and statement. So I need 3 whole numbers that are in between 4 and 9. There are several, but I'm going to do 5, 6, and 7. Whole number solutions to the or statement would be whole numbers less than 4 or whole numbers greater than 9. I'll do, let's say, 3, 10, and 11. 3 is less than 4, 10, and 11 are greater than 9. It says which is best described as having solutions between two values, the and statement or the or statement. That's the and. Again, I think of and sandwich. It's in between two pieces of bread, in between two numbers. So and. It says the shaded region in each Venn diagram represents the solutions to compound inequalities. Label them either or and. Now, Venn diagrams, it's when we have circles or ovals or bubbles that are either overlapping or not. So here we have two separate bubbles, no overlap. So that would be the or statement. But in this Venn diagram over here, we have an overlap. That overlap is where both inequalities are true. Okay? There's another word that we use for these two. When we have a Venn diagram or a set of solutions that are separate from each other, we call this the union. The way I remember it is that if I have two separate solutions that I'm trying to write as an answer to one question, I have to join these two sets together. Those two sets together are my answer. But there is no actual connection, so I have to kind of bring them together. I have to make a union between them. Here we call this the intersection. Intersection is where two things cross or two things touch. Well, there you go. It's kind of self-explanatory. Those two solutions cross and touch right there. Now, in the next page, you're going to see a notation, a way to write these things. And that notation that we use to mean union is just a big U symbol. To mean intersection is an upside down U. I don't know why, I don't know who came up with it, but that's just the notation that we use. So here we go, here's that notation. So here's the and. Again, this means intersection. And the or, that means union. You see these symbols a lot again in functions where you have graphs and there's maybe more than one on the same graph. We'll talk more about it later on in the course. So our steps are, when we have a compound inequality, solve each individually, graph them above the same number line, and if you have parts that overlap, that will be and. If you do not, and they just go in separate directions, that's or. So here we have 2x is less than 8 and 3x plus 2 is greater than negative 4. They solved the first one for us. They divided both sides by 2 to get x is less than 4. And on the right, they subtracted 2 from both sides, then divided by 3, and got the solution, x is greater than negative 2. So here is this notation. Now, you have not seen this before, so let me explain what you're going to see right here. These curly Q brackets just mean this is one part of the solution, and this means all x's such that x is less than our answer that we got, which was 4. Okay, this little bar, again, I don't know who came up with this, but we do use this quite a bit in upper levels of math. So we will continue using this notation from here on out. So all x is such that x is less than 4. Intersection, that upside down U symbol means intersection. X is less than negative 2. Or another way to write it, instead of using the intersection symbol, is what we talked about with putting it together. Now, my smaller number is negative 2, so that should go on the left. My larger number is 4, that should go on the right. Now, if you're unsure about it, think about what this means. X is in the middle, x has to be bigger than negative 2. Well, that's what this part is. X has to be less than 4. That was the beginning part. Now, if you look at the graph, This top one was x is greater than 2. I'm sorry, greater than negative 2. This bottom one here is x is less than 4. The overlapping is that solution there, in between negative 2 and 4. So let's take a look at B. It looks like we're going to have an OR compound inequality. So it looks like they start by subtracting 2 to get to this step, then divide by 3 to get that step. Then they subtract 4 here, divide by negative 1. Now notice, what happened to these inequality symbols? They flipped. When you multiply or divide by a negative, that turns the inequality symbol. So, if I were to fill in the notation, this means all x's such that x is greater than or equal to negative 1, union, meaning I'm pulling the two solutions together, x such that x is less than or equal to 2. So let's take a look at what this does. Let's first graph x is greater than or equal to negative 1. So if it's greater than or equal to, that means I have a filled in circle. Greater than means I'll go this way to the right. Less than or equal to 2, here is 2. And then I'm going to go this way. Now this is an interesting situation because with what we talked about in the previous page, we had two Venn diagrams that didn't overlap. Okay, well look at this. We have a section right here that overlaps. That is included in our solution. So union means we're pulling together all solutions. Intersection is just where they overlap. So we need more than the overlap, we need the whole thing. And guess what? It's the whole entire number line. And I just do those little squiggly lines when I go over a number line so you can see it better. So this means this is the set of all real numbers. Really, if you just say all numbers, I'll know what you mean because we haven't talked about anything that's not real numbers. In Algebra 2, you talk about imaginary numbers, but we just use the phrase all real numbers. All right, so C. Let's see about this one. All right, so we add 3 first, divide by 2. We didn't multiply or divide by negative, so no flipping the sign. Here we just subtract by 4, and then we've got x is less than or equal to negative 3. And this is an and, so we're going to be using an intersection symbol. X is greater than 3, x is less than or equal to negative 3. So let's see this. Here is negative, if I'm going to do, let's see the first one, greater than 3. Here's 3, open circle because it doesn't have the equal to, over to the right. And negative 3, but filled in because it has the equal to, less than to the left. This is intersection, this is and. So here again we have another unique situation. Intersection is looking for the overlap where both solutions cross. Do these solutions on the number line cross? No, they do not. So that means this is a situation where we have no solution. When we have no solution, we call this the empty set, or a 0 with a cross through it. What that means is there's no solutions. There are no numbers that make x true. So far we've had just a normal situation. Okay, the very first one where we have an overlap, we solve, we get a solution, all x's in between negative 2 and 4. Then we had a situation with OR union where when we take the joining of both solutions, we get the whole entire number line, all real numbers. Then here we had no overlap when we're supposed to find the intersection where the solutions overlap. So that's no solution, or the empty set. Let's see what happens here. So we add 1 from here to here, divide by 3. Okay, subtract 2, divide by 2. All right, and we're at OR, so we're talking about union. Greater than 1, greater than or equal to 3. So let's take a look. 1 is here, greater than To the right, 3 filled in circle to the right. Okay, here's another unique situation. Union is not the intersection or the overlap. Union is the joining of the two solutions. So if we join the two of them, then the true solution happens to be the greater than 1 solution. Because if I join those two, then this one just kind of becomes part of the first one. So my answer is just all x's such that x is greater than 1. So in part C, why did we get the empty set? We got the empty set because in and we are looking for the overlap. There is no overlap. So let me write that down. Okay. Then in 1b, why is the solution greater than 1? It was because union is the joining of the two solutions. So if you join the two of them, then it really is just x is greater than 1. So since x is greater than or equal to 2 is included in x is greater than 1, let me just make sure I have those right. Oh, it was 3, not 2. Same thing though, anyway. Oh, I keep writing with my sweater. There we go. Okay. So since x is greater than or equal to 3 is included in x is greater than 1, then we only need x is greater than 1. Okay? So that's compound inequalities. Now, what we're going to do is we're going to join what we just talked about with compound inequalities and what we know about absolute value. If you don't remember, absolute value is distance from 0. Okay? So if I want, let's say, the absolute value of, say, -3, what that's asking is how far is -3 from 0? Well, it's 3 units. So absolute value of -3 is +3. So what we're going to do in this activity is we're going to discover how we write an inequality using that has or involves an absolute value. So we're completing this table, and all we're doing is taking the x value and taking its absolute value. So we're doing the absolute value starting with -2.5. How far is -2.5 from 0? Well, it's 2.5 units. How far is -2? 2. How far is -1.5? 1.5. 1, 0.5, 0. Now these, the positives, they're just the number. Okay, they don't change. So if you notice, when I take the absolute value of the negatives, I get positive. So I have basically 2 possible numbers that have the same distance from 0. We already know that. When I talk about or I ask what number numbers are 2 units away from 0, there are 2 answers. -2 and 2. Okay. So then what they want us to do is circle all the values of x for which the absolute value of x is less than 2. So 1.5, that's the absolute value of -1.5. That is less than 2. This is less than 2. This is less than 2. 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 Whoop. Have to stop. If it said less than or equal to 2, then I could circle these and these. So all of these x values here, when I take the absolute value of those values, they will be less than 2. So let's put that on a number line. So I've got negative 1.5 is my first, 1, 0.5, 0, 0.5, 1, 1.5. So then it asks, is negative 1.9 included in the shaded region? Why or why not? Well, is the absolute value of negative 1.9 less than 2? It sure is. Absolute value of negative 1.9 is positive 1.9, because negative 1.9 is 1.9 units away from 0. Well, that's less than 2. So I can include negative 1.9. Are 2 and negative 2 included? Well, is the absolute value of 2 less than 2 units? 2 is exactly 2 units away from 0. 2 is not less than 2. So it is not. So what do you think that means? When we've used number lines to represent numbers that approach a certain value but not include that value, we use an open circle. So I would have open circles at 2 and negative 2, and then everything in between them would be part of the solution. So what did we just talk about? We just talked about in the previous section compound inequalities. Compound inequalities could look like what we just gave or what we just drew on this number line. So try and think, while we talk about some other things, try and think about what type of compound inequality that might be. So, number 6 is, what can you say about the distance of x from 0 on the number line if you know that absolute value of x is less than 2? That means the distance must be less than 2. So here we go. Here's that compound inequality. Describe the region you shaded using a compound inequality. Well, are we talking about in between two numbers, or sandwiched between two numbers, or are we talking about opposite? Here we're talking about sandwich, so this is and. So I could write it this way. I could either write x is greater than negative 2 and x is less than 2, or we can write it the preferred way like this. So the smaller numbers on the left, larger number on the right. Now here's an interesting question. How do you think the shaded region would be different for the inequality instead of absolute value of x being greater than, or I'm sorry, less than 2, less than or equal to 2? Well, it's really not going to change it a whole lot. It's just going to fill in the circles. Or I'll call it fill in the endpoints. So on our number line, we would have something like this. Negative 2, 2, filled in circle, fill in circle, shaded in between. Okay? So what this means is when I have an absolute value involved in an inequality, it will automatically become a compound inequality. If you think about what we've learned already about absolute values, this makes sense, because absolute value has two solutions most of the time. So here's another example. It says solve the inequality, draw the graph of the solution set on the number line. So if I solve, first thing I want to do is get absolute value by itself, like we did when we talked about absolute value. So this is saying what number or numbers are going to be less than 3 units from 0. Think about it on the number line. So here is 0. Well, 1 is less than 3 units away from 0. 2 is less than 3 units away from 0. Negative 1 is less than 3 units from 0. Negative 2 is less than 3 units from 0. But where I have to stop is negative 3 and positive 3. So this is going to be one of those solutions where I'll have open circles and then everything in between. So that's what it would look like, and doing it this way, graphing it on the number line, that will help you figure out what type of compound inequality it is. When we have a number line where we're shading in between or drawing in between two values, that is and. So it's and. Because the solution is between two values. So we could write the solution to this as all numbers between negative 3 and 3. Take a look at this one. This says less than or equal to, but it says absolute value of x plus 2. Not like what we had before. So I can't take that 2 outside of the absolute value. We can think about it on a number line, but it might be pretty difficult to do so. So it says, what number or numbers could I add 2 to those numbers and be 5 units from 0? Well, let's think about it. What could I add 2 to and be 5 units from 0? I know one, 3. Since it says equal to, I can include that number. What other number could I add 2 to and be 5 units from 0? That would be negative 7, because negative 7 plus 2 is negative 5. I can include that and then shade in between. Okay? So there we go. There's our answers here. So I could write this as negative 7 in between negative 7 and 3. And here I include the equal to parts because I have the filled in circles. Now here is another way that you could write this. So if you think about the two cases of absolute value, we can set it up x plus 2 less than or equal to 5 without the absolute value, and x plus 2 and then negative 5. Do you remember when we did this with our equations? Well, this time we have inequalities. What did we do with the inequality symbol when we multiplied or divided by a negative? We flipped the sign. So it's not going to be less than or equal to anymore. It's going to be greater than or equal to because I changed 5 from positive to negative. In a sense, I multiplied 5 by negative 1. So subtract 2. There's one of my solutions. Subtract 2. There's my other. So again, if I were to write this as compound inequality, negative 7 is my smaller number, so that should go on the left. I get the same thing. So you can either think about it using a number line and using what absolute value means, or you can use this process of splitting it up. And that's what this kind of gets at. So the top part is talking about the process. So in this very simple case, absolute value less than 5, we're going to have an inequality, a compound inequality, where I have negative 5 on the smaller side, 5 on the bigger. And then on the number line, I'm looking for the two numbers that are less than a certain unit away from 0. So in this case, if we're talking about absolute value of x is less than a, then I'm looking for the two values that are a units away from 0, and that's a and negative a. Okay, same properties are true for the symbol less than or equal to. It's just filled in instead of open. All right. Now what if instead of less than we have greater than? So let's see what we get here. We're going to do the same thing as we did on the first page of this section where we filled out the table. Absolute value of 9 is positive 9 because negative 9 is 9 units from 0. No, I'm sorry. Let's get positive 6, positive 3, 0, 3, 6, 9. So then I'm going to circle all the values that are greater than 3. Here's one. Here's 1. 3 is not greater than 3, so I can't circle it. 0 is not greater than 3. Okay, so then 6, 9. So when I plot these on a number line, I've got negative 9, negative 6, 6, and 9. So if we shade in here, what values that make the inequality true? If you think about it, absolute value of 7 is 7. That's greater than 3. Absolute value of 5, negative 5 is 5. That's greater. Absolute value of negative 4 is 4. That's greater. But again, absolute value of negative 3 is 3. It has to be greater than, not equal to. So open circle. Absolute value of 2 is 2. 2 is not more than 3 units from 0, so I can't include those. So it looks like I'm going to have one of those situations when we talked about compound inequalities where it's going opposite directions. That is an OR compound inequality. Or compound inequalities are written separately. So one of my solutions is x is less than negative 3. The other one is x is greater than 3. Okay. Now let's do these other examples. I want to get absolute value by itself first. 6. Then I can either split this up and think about the two cases, remembering when I change 6 to negative, I flip the inequality symbol. Or I can think about what this means on the number line. What numbers could I take away 8 from and be 6 units from 0? I'm going to do it the process way. So if I do this, that's the regular one. Here is where I'm going to need to flip the symbol. No, that's the same way. And make 6 negative. Add 8, get 14. Add 8, get negative, positive 2. Positive 2. So on a number line, it's asking me to have numbers that are less than or equal to 2 and numbers that are greater than or equal to 14. So let's take a look and see what that looks like. So I've got 2 here, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Probably could have maybe done with a little bit more room there. So maybe I'll move it here. So let's say, let's make that 2. So that's 0, 4, 6, 8, 10, 12, 14, 16. Okay. I can fill in 2 because it says equal than. Less than would go this way, to the left. 14, it says equal to, it says greater than, and that's going this way. So what should I join, or what word should I write in between those two inequalities? And that word is OR. Because my number line, the solutions are going in opposite directions. So when we write the solution, if they asked, and we didn't do this for some of the earlier ones, but I want to remind you how we could write the solutions using the curlicue brackets. All x's such that x is greater than or equal to 14, or is union, x is such that x is less than or equal to 2. Okay. Now let's take a look at number 2. Start by subtracting 1/2. That'll give me 3 1/2. split this up. Subtract 2.5 from both sides, I'll get 1. Subtract 2.5 from both sides, I'll get -6. -3.5 minus 2.5 is -6. So then if I graph this, -6 is my smaller number, -7, -6, 5, 4, 2, 0, 2, 6. Okay, that'll work. So can't include -6, open. Less than means this way. 1, can't include 1, open. Greater than means this way. So here again, this is an OR. And if I write this with the set notation, the curly Q brackets, all x's such that x is greater than 1, union, all x's such that x is less than -6. Okay, and I'll try it if we have a quiz or a test. I'll try and put on there, please write your answer in set notation. If I say that word or that phrase, set notation, it means what I just wrote here for these two. So here again, here's our general rule, if you're thinking about it in terms of rule. When I have greater than, it's asking what values of x have an absolute value greater than a, whatever your number value is. I remember it this way. Greater than. And then the one before, less than. Less than. I know it's dumb, but less than. It helps me remember. Or some people go land of Gore, which I think is even dumber, but if it helps, that's what's important. Okay, so let's take a look at some special cases. I would subtract 7 from both sides in this one and get -5. Before I go about solving this, I want us to think about what this means. It says absolute value of 2x plus 12 is greater than -5. Honestly, it doesn't matter what's in the absolute value because absolute values always are positive. Doesn't matter what I put in for x. I could put 1, 5, 1 million, doesn't matter. I could put -1,000. When I take the absolute value, the answer will be positive. This is always true or infinite. Actually, we wrote it as all real numbers on the other page, so that's how I'll write it here. So when I draw that on the number line, guess what? It's the whole darn thing. So what do you think this one's going to be? Probably the no solutions case, but let's just see. I would start by adding 5. That'll get me -1. Now, I'll divide by 4. Got to do that first. Got to get the absolute values by itself before I decide what type of solution it is. Oops. Okay, this is still a negative value. So, in both cases, in these examples 1 and 2, we had a negative value on the other side of the inequality symbol. But here, the inequality symbol makes a difference as to whether it's all real numbers for solution or no solution. If we think again about what absolute value means, it means distance from 0. Distance from 0 is always positive. Are positive numbers less than or equal to a negative number? 1/2. No, they are never less than a negative number. Positive numbers are greater than. So this won't work. So on the number line, there is no, I shouldn't shade anything. So you can put, that means the empty set. Okay, the 0 with the mark through it. Which you could have also done, which I should have shown you this earlier. It just came to my mind, came to my attention. Which you could have done here for this one for set builder notation. I'm going to write it, and then I'm going to explain it. This probably looks like Greek, and some of it actually is. What this means, if I were to say this in words, is all x's such that x is an element of the real numbers. This means real numbers. This means an element. You get more into this notation in upper levels of math, so it's important that perhaps you see it, but if you're writing a solution and it's all real numbers, you can write it this way. Now, it may not seem like it's quicker, but it's up to you. But if it says write your answer in set builder notation or set notation, then you would need to write it this way. Let's take a look at an application. It says some fire extinguishers contain pressurized water. The water pressure should be 162.5 psi, pounds per square inch, but it is acceptable for the pressure to differ from this value by at most 12.5 psi. Write and solve an absolute value inequality to find the range of acceptable pressures. Graph the solutions. So, when we've set up absolute value applications before, we have put x minus whatever our given value is, which in this case is 162.5. What goes on the other side is how much it can differ, and that's this value right here. Since we've been talking about inequalities, we need to use an inequality symbol, and we get that inequality symbol from this phrase, at most. That means 12.5 is the maximum, so everything on the other side has to be less than. This is a less than inequality, so this will end up being an and compound inequality. So when I set up, here's my regular. When I make 12.5 negative, that's when I have to flip my inequality symbol, add 162.5, and that will get us 175 psi, if I did my calculations correct. I think so. Okay. And then here, if I add 62.5, that's going to be, I think, 150 psi. Yeah. Okay. So when I put this on a number line, since this is an and, that means that my solutions are going to be in between these two values, 150 and 175. Now, whenever you do a number line, you can use a different scale instead of going by ones each time. I'm going to go by 25s. So 125, 150, 175, 200, 250. Sorry, 225. So I can include 150, I can include 175, and there's all the values in between. So if I were to write this in words, my answer would be the pressures can be between 150 psi and 175 psi. So, what we've talked about are compound inequalities and absolute value inequalities. Absolute value inequalities are compound inequalities. Their solutions are and or compound inequalities. And inequalities are talking about an overlap or an intersection of two solutions. Where are both solutions the same? Or compound inequalities are talking about union. Union is the joining of the two solutions. So keep that in mind when you do this. And also don't forget, in any absolute value or compound inequality, if you multiply or divide by a negative, you must remember to flip your inequality symbol. So here is the assignment. Now, these workbook pages come from the red workbooks that I have in my classroom. If you were here for this lesson, you should have gotten one of these workbooks. If you were not here for this lesson, then you're going to need to pick up one of those pages the next time you come back. But section 2.7, the assignment is from the textbook, so you should be fine there.